Alright, this is Mark Anderson for Kellogg Community College, and today we're going to just do some basics about the introductions to logarithms here. The first thing I'm going to do is I'm going to make a graph, I'm going to make a table of this information here, and I'm going to put some values down for x. Let's start off with 0 and maybe go to 4, right? So if I do that and I plug a 0 in for x, my y value is going to be a 1. If I plug a 1 in for x, my y value is going to be a 2. And then 2 to the second power would be 4, 2 to the third power would be 8, and 2 to the fourth power would be 16. So you can see as I progress, these y values are going to double every single time. So this is an exponential. The graph would look something like this, crossing at 0, 1. And what this represents is me switching the x and y. Now when I switch the x and y, this is called an inverse. The inverse is when we switch the x and y positions, and what this would give us is our x is now 1, 2, 4, 8, 16, 32, and our y is going to be our 0, 1, 2, 3, 4, 5. If we were to graph these points, and we will actually be doing this in a later unit, what we would get is this inverse graph that looks something like this. This graph would not touch the y-axis, just as this did not touch the x-axis. So what this is right here is your first logarithm. So what is a logarithm? Logs are the inverses of exponentials. And in the series of videos here that's going to talk about section 2 of the unit that we're in, I am going to try to give you the best chance to learning logarithms by just having you play around with logarithm formulas and concepts in general. And then by the time we get to the third or fourth section, we'll actually be into solving with logarithms. So let's start off with the idea that logs are the inverses of exponentials. But what I have to show you here is I have to show you that this is the exponential function and this is the logarithm function, and I want to show you some equivalencies here. First of all, this letter b here at the bottom, this is the base. This is the language of the exponential system that we're in. So if we had, for example, y equals 2 to the x, our base here would be 2. So that means that we would move by doubling at each stage or interval of the problem. So 1, 2, 4, 8, 16, 32, 64, 128, so on and so forth. This right here is the stage. The stage is like the unit unit of x that this is being multiplied by, and the y is going to be the result. It's the result of raising that base to that stage. So these kind of are in the same, they're in different places with the logarithm notation, but the base will always be in the corner of the log. The y is going to be our result if we were to plug in for x the stage of the exponential that we're at. So y equals 2 to the x is equivalent to saying log base 2 of y is equal to stage x. In this problem here, we got log base 3 of y would be the result if we had the power of x, which is 2. Now, it's interesting that we can actually take a look at this problem because we know 3 squared is 9. So 9 is equal to 3 squared. Well, this is saying then that if I have log base 3, that in base 3 the answer is 9 if I raise it to the second power. And so I can convert this way here. See, log base 4. My result is 64 if I raise it to the third power. So you may want to try translating this in words here. You could say like in base 4 you get 64 if the power, stage, or exponent is 3. And that's true. 4 to the third power is 64. Now I want you to kind of convert this back. Now what I would always do if you're converting back from logarithm to exponential notation is I would start off with the base. In this case, the base is 5. The exponent is x, and this would give me a result of y. Here, the base is 2, the exponent in this case is going to be 4, and that is going to give me y. What's interesting about this is we can figure this out. 2 to the 4th power is 2, 4, 8, 16. So this problem is saying in base 2 you would get 16 if you raise it to the 4th power, or base 2 to the 4th power. Now here our base is 5, our power is going to be x, and our answer is 125. We could solve for x because 5 to a clean, even integer is going to give us 125. In this case, it's going to be 3. So why do we teach exponentials and logarithms in the first place? Because, I mean, if we have an exponential, we could solve those just as easily as logarithms. In fact, perhaps easier. But there's a catch. So let's talk about the catch. We're going to look at base 3, and base 3 is going to have several easy to find answers, and one really difficult to find answer. So in this case, if we were to solve for x here, we would just kind of mentally think 9 is equal to 3 to the what stage? Well, the answer for x is 2, because 3 to the 2nd power is 9. Here, 27 is equal to 3 to the what stage? Well, pretty easy logic to follow. 3 to the 3rd power is 27. And 3 to the something's power is 81, so the answer is 4 there. So now becomes the question, 3 to the what power is 50? And that's tough, because we actually know the pattern of multiplying by 3 in an exponential pattern from, stage 1, 2, 3, and 4. Like, for example, this would be 1, and then 3, 9, 27, 81, and then 243. But 50 is somewhere between 3 and 4. But we don't know the exact value of it. So we cannot get an exact answer for 50 equals 3 to the x power, not without logarithms. Because at this stage you might be saying to yourself, well, I'm just going to get the x by itself. Well, how are you going to do that? Divide by both sides by 3? Multiply both sides by 3? Those are not the inverse operations of an exponential. So what I'd like to do is I'd like to go back to 1a. So this is going to refer to like this 1a, 2a, 3a, 4a. They're going to refer back to these 4 problems right here. So if I was to convert this into log notation, my base would be 3, my result would be 9, and my answer would be x. Note that the x is now all by itself. Alright, now here in my log base 3, my answer would be 27, and that would also be equal to x. So by converting this into this, I can now get the x by itself. Whereas up here, if you were trying to get the x by itself, you couldn't do it, not without the power of logarithms. Here, log base 3, to get to 81, is going to be equal to 4, or x in this case. Now, finally, this last problem, this log base 3, to get to 50, well, unfortunately we still can't get our answer here, because I haven't taught you something called the change of base formula. But we're going to get to the change of base formula by the end of this section's multiple videos. But what this did, so take a look at this problem. What this did is this x was not by itself, but here the x is by itself. So if we can somehow process this log base 3 parentheses 50, if we can somehow process that, we could get the answer for x. And the answer is the change of base formula. And we're going to learn that again at the end of the series of these videos, where we learn about how to manipulate logs. So in the conclusion of this video, m equals log base a of x is equivalent to a to the m is equal to x, or base stage result. Thank you for watching.